Hi, Bob Sterner here, and in this video I'm going to present the first of several very simple mathematical models of lake loading. We do this exercise not so much because the mathematics is that important by itself, but because exploring this concept thoroughly, quantitatively, and precisely like you can with a mathematical model will greatly enhance our understanding of the principles involved in lake loading and how we manage lakes for water quality. We're going to start with a lake, which we represent by a box. There's our box, which is our lake. And this lake has fixed volume V. And we're using the units meters cubed in this case for volume. This lake has one inflow and one outflow. With fixed volume V, the hydrologic flux in must equal the hydrologic flux out. So we'll use the symbol Q for flux of water, meters cubed per second. And another assumption we're going to make about this lake is that its contents are completely and instantaneously mixed, meaning the concentration of substances at any one moment anywhere in the lake is identical. We're going to pay attention to two concentrations in this model. We have the concentration of substances in the inflow. This is essentially our loading, which is what we're interested in here today. So Ci is the concentration in the inflow with units moles per cubic meter. And the concentration that we're ultimately most interested in is the concentration of substances in the lake. We represent that with the symbol C, also moles per cubic meter. Now, the assumption of complete and instantaneous mixing also means that the concentration of solute in the outflow will equal the concentration in the lake. So the concentration in the outflow is also given by C. So that's our complete description of this very, very simple lake. One inflow, one outflow, complete mixing. Now that we have our first very simple model of lake loading, let's see what that model has to teach us. The first thing we need to do is recognize that the quantity, the mass of substances within the lake will be given by its concentration in moles per cubic meter times the lake volume in cubic meters, giving the units moles. And what we want to do is ask how that mass of substance in the lake varies with time, or rather, what is the time derivative of dCV dt? The time derivative of the quantity of substances within the lake will be given by the rate of inputs, which is given by the concentration in the inputs times the hydrologic flux Q. This quantity also has units moles per time, as does the time derivative on the left of the equal sign, minus the outputs, which is given by CQ, the lake concentration, which is equal to the outflow concentration, times that hydrologic flux Q. Now you may recognize that dCV dt is the derivative of a product, C and V, and you may remember the product rule from calculus. And if you do, then you'll also recognize that we have said that the volume V is fixed, and therefore its time derivative is 0. And as a consequence of that, the thing that we've just written for dCV dt is also equal to the time derivative d of lake concentration, dC dt. And that's the thing we're interested in. How is the concentration of some nutrient or pollutant in the lake changing over time? The easiest thing we can do with this model is to ask what happens at steady state, when the concentration is no longer changing. This is effectively what would happen over a very long period of time, essentially infinite time, given the assumptions we've made about the model and that nothing else changes. At steady state, dC dt equals 0, and therefore the thing we've written, CIQ minus CQ, is also equal to 0 at steady state. We can solve for C, which is what we're ultimately interested in. And what we find is that the concentration of stuff in the lake comes to equal exactly the concentration of stuff in the inflow. There's really nothing else that can happen in this model because there's one inflow, one outflow, complete mixing. Given time, the concentration of materials in the lake, so concentration in the lake versus time, will come to equal a value equal to the input concentration, the inflow concentration. So if the lake starts out with relatively low concentration of substances, over time, that concentration increases and levels out to where it equals CI. If we start out with a higher concentration of substances above the input concentration, over time, the lake dilutes out and eventually reaches the same steady state, CI. This very, very simple model of lake loading says that whatever concentration of substance we put into the lake is the concentration we will eventually see in the lake given enough time. Effectively, the lake concentration exactly reflects what the watershed is delivering to it. This model is unrealistic in many, many ways. Probably some of them you've already thought of, but we want to use it as a starting point, as a benchmark. So we present it not because it's the right way to think about lakes, but because it is a good foundation for us to think about some other things that are more realistic. We'll do that next. So that's it for this video. Simple loading model number 1. Talk to you later.